cover those on Wednesday. On Monday, we're doing exam number 3, and that will be in lab, so that you have a little more time to interpret the C13 and the mass spec. Those take a little more time, just to work with the graphs and things. So we'll be looking here at about, typically we do about an hour and 40 minutes or so, and then we'll take the other half of lab, and we'll do the azo dye lab and get partway through that experiment. Okay.
For the amine synthesis, I was going through a couple of problems, and you can do a couple of them without amines at all. Is that okay, or?
Yeah, as long as whatever you do is correct, but be careful. Are you doing like an SN2 and then reduction, that kind of thing?
I don't know.
So you're not using. I'm a little nervous about making an amine without using an amine, so it shouldn't be. As long as what you do is right, okay. Okay. As promised, we're going to continue a little bit on the diazonium salts. I'm going to talk to you guys about azo dyes, which is a section in the book, actually in lab. It fits better with the actual lab, so we'll talk about that on Wednesday in lab. But what I'm going to do is one more synthesis problem with these guys. We saw that N2 plus can be turned into a couple of things, and I gave you guys a chart. Yes. But we saw where you can turn it into a bromine, you can turn it or into a chlorine, so you can turn it into a halogen with the correct reagents, or an IV. Put all the halogens together. We saw where you can turn it into nitrile. So you put a CN on there, and that reminds me, I need to show you a reaction. This would be helpful to you. And you can turn it into an OH. And then, this is one we're going to play around with today, you can completely get rid of it, which seems a little weird that you would put a group on only to get rid of it. And we'll be doing that in the next synthesis problem we'll do, because we're going to essentially use an NH2 and an NO2 for directing effects only. Put other groups on, and then shoot them off when we're done. So it's pretty valuable. To get to it, what's helpful with this is you get to the diazonium salt by taking aniline, or a derivative of aniline, and treating it with, do you remember what it is? Yeah, NaNO2 and HCl. So what's nice about that is that one step before the diazonium salt, you have an orthopara director. You could direct things orthopara. But let's say you needed a beta director. Well, you actually have that too, because one step back from that, you put on an NO2. And this is a beta director. So this is really a pretty powerful sequence. You can put a group on, you can direct meta, assuming you're not doing photographs. You can direct meta. Then you could change it, you could direct orthopara. Then you can take the group that's on there and either get rid of it or change it into something else entirely. So it gives you a lot of flexibility that we didn't have before. So we saw a pretty simple example last time, which you have in your notes. I'm going to do something a little more complicated and show you some of the problems that you could encounter as you're going through this process. There's things you have to be careful of. But before I do, I want to show you one reaction that will help you, I think, on your second synthesis worksheet. That there are some of them where on the problems, as I remember, you have a carboxylic acid in there, right? And so far, you guys can put it on with aldehydes, put on an aldehyde or a CH3, an alkyl group, and oxidize. But you can go from a nitrile to a COOH by just H3O plus heat. So that reaction right there, put it in your notes, because it might help you out on the synthesis and save you a couple of steps as you go through. Okay? We're not going to learn the mechanism of it today, because it is something we're going to tackle in great detail in the next unit. So just remember the reaction for right now. There we go. Well, that goes in the dark. Okay, so here we go with our second, little more complicated synthesis. What I want to do is because I need a bromine to be better. So just doing this in one swoop is not going to work at all. What we could normally do is, let's say that we're just an alkyl group here that was not a nice propyl group. I could fool around with it. If this branch were not here, put a carbonyl there. Then that's a meta director, and then change it back. Right? That's kind of the trick. That was my previous example was that, and then before you some class before you guys figured it out in a second. So I have got you stuck. You cannot make a carbonyl out of that, so I did that on purpose. Okay, so you can't change it into something that's a meta director and then change it back. So you have a problem. So what we're going to do here is we are going to put on an ortho para directing group. Use it, and then get rid of it. So kind of the synthetic plan is I'm going to take this guy, and my isopropyl is still there, through a series of steps, put on an NH2. And it's not going to be one reaction, it will be a series of things. This is a very strong activator, ortho-para-directing. So then what I can do is do a bromination. And it will go there. And then in the last step, I'm just going to put minus NH2 in quotes because that's really going to be a little more complicated. I'm going to just get rid of it. So the only reason I have that group there is to force a reaction that I need to go where I need it. But I don't actually want that group there at all. Okay, so this is an example of using it and getting rid of it. It's also going to illustrate a small problem that we're going to run into as we go along. And I'll show you guys how to fix it. So, here we go. I have to put an NH2 in the para position. So, starting with styrene, how am I going to do that? How am I going to put an NH2 right there? Add an NO2, good. So, HNO3, H2SO4, and NO2. And then what do I do to turn it into an NH2? It's a reduction, right? Sort of the question is kind of what don't you do? But let's just pick something OAH. How does that sound? NH2O. The only thing you really could not use would be sodium borohydride. It won't do the trick. But you could do H2, you could do any reducing agents. So now I've got an NH2. And this guy, it's worth noting, is a very strong activator. It's really, really good. So, let's say that I go and I bromine ER2, FePr3. I am likely to have this happen. It's going to direct ortho-para. It's the stronger activator, much stronger than the alkyl group, so it's going to drive where the reaction goes. And I will get that, which is great. And it's such a good activator, I will get that, which is not so great. So the problem is it was too good. And that's a typical problem with NH2, is it does too much. So, and also sometimes if you're using, say you do something acidic here, I think I asked you guys a test question or something about this. This can turn into NH3+, and then it's a meta director, okay, which is a problem. I think that was a Unit 1 question on a test. So having an NH2 there kind of by itself doing its thing can be a real problem. And so what you'll see oftentimes is that before you do the next reaction, what we're going to do is kind of calm it down a little bit, if you want to think of it like that, sort of protect it. And so what people will often do, they won't do a reaction with this because it's just out of control. They will treat it with something that will acylate it. Typically, really common, is acetic anhydride. So I'm going to take an amine, treat it with acetic anhydride. We'll learn the mechanism mechanism for this in the next unit. But what happens is this group right here is placed onto the nitrogen. And we end up with this. We have NHC CH3. So we make an amide. Now there's still a lone pair here. It still is an activator, it's still an ortho-para activator, but it is polymer. It's not strong. Why would that be?
Because the electrical density from the suitable low down.
Yeah, with NH2, my lone pair has nowhere to go but into the ring. Right, so it's donating full lone pair into the ring. Here though, this lone pair can go into the ring, still can do that, but it can also go into the carbonyl. So that electron density, you might think of it as a cloud, is not entirely skewed into the ring. Okay, so it's not quite as active. So now, what we've kind of done is calmed it down, and when we go ahead and do the next reaction, it's much more controlled. It will just do it once. It's not going to do everywhere. And we get just one addition. So it's kind of a little sidestep that you'll see in synthesis that will be taken to keep the reaction from doing just one addition. Okay, so if you look at the molecule that we've built now, I've got the pieces that I need there. Everything I need is there. I have got this part built. And that's what I wanted. Now I have to get rid of the amide. So we're going to do two things now. The first thing we need to do is we need to deprotect. And to do that, you can just do OH minus H2O to heat. That cleans the amide right off there. And then we need to remove the NH2 that's remaining. I just have to get rid of it. So let's go ahead and go through that series right here. I'm going to redraw it. So, to deprotect, OH minus H2O to heat. That puts us back where we started with an NH2. And now I want the NH2 to go away. And the effective way to do that is go through diazonium salt, which then I can turn into an H. So how do I make the diazonium salt? NaO2HCl. Now look back in your notes. What is going to make this thing turn into an H? It's an H. Wasn't it H3PO2? Okay, yeah, hypophosphorus acid. And that will remove the diazonium salt. Put an H right there. And it gives me my product.
H2O keeps to make the alcohol instead?
If you wanted to make an OH right here,
Yeah.
H3O plus a B. Yeah. Sometimes you'll see just H2O. It depends what book you're looking at. H3O plus a B is pretty common. Yeah.
So if you brominated with the NH2 on it, would the NH2 also have that?
You know, it could, because it's a base and FeBr3 is a Lewis acid. And so it could. So typically people will make an amide and then do the reaction because you end up with a lot less conversations. Okay? So you guys will find on a few problems on that homework that this is a pretty effective way to do what you need to do. Okay, and also don't forget that reaction where the CN, the nitrile, can turn into a carboxylic acid. That'll help you too. All right, so That ends amines with the exception of the azo dyes, which we'll look at next time. So we're going to start into mass spec now. I like mass spec, it's fun. Yeah.
Can we use acetic chloride instead of acetic?
You can, yeah, you absolutely could. Another thing, the question was, acetic anhydride's common. You can do acetyl chloride too. CH3, C double bond Cl. All right. Let's go ahead and do mass spec. Mass spec is interesting. It's a giant puzzle. For the exam, don't forget your calculator. You'll need it. Okay. First thing about mass spec, I put up a note yesterday, the day before, about watching a little movie. It's available. It's on D2L. I'm not going to show it here. The movie's longer than what I want you to watch. They go into some more detailed stuff that we're not going to do. But I think there's a note on D2L to watch about the first 6 minutes and 30 seconds of it. That's the general stuff. And then after that, they get weird, so I don't want to do all that. But take a look at that. It's a good explanation. It actually shows the real instrument and shows you where the things are happening for real that we're going to be talking about today. So sometime next week, look through that. Now, as far as mass spec goes, normally what I do is I shine the spectrum on the board and kind of draw all over it. Can't do that in this room. So we'll kind of muddle through. We'll have the spectrum up here, and then we'll be drawing fragments there. Okay, you'll just have to match the fragments to the spectrum as we go through. A couple things about mass spec, just as way of introduction. One of the important pieces of information that it can give you, doesn't always, but it could, and often it does, is the molecular weight of the sample, which is really good because if you're making something totally new and you put it through mass spec, if you know kind of what it is you're supposed to have made, it's going to have a certain molecular weight. And if what you get back matches what you say it should be, that's a good sign that you probably did make what you wanted to. One thing that is really nice about it is the sample will be really small. When I was doing my research, my infamous 12% yield, I did not have a lot of sample to send over for a mass spec. And I would do an IR, and I would do an NMR, and all that stuff. And what I would have left, literally, look at a vial, it wasn't even a drop. I'd look at a vial and hold it up, and I'd say, there's something on the sides, and just shoot over what looked to everybody else like an empty vial. And they were able to take that sheen of oil on the sides and actually get a mass spec off it. So you need really, really small samples. You don't need much. It is the first kind of spectroscopy I think we've run into where it does not absorb some kind of electromagnetic radiation. IR we had infrared light, NMR radio waves. This doesn't do that. What it does is it shoots electrons at the molecule, and it's such a high energy beam, it knocks an electron out of the molecule, which makes it a radical, and then the molecule explodes. So it's not something where you're not going to shoot your sample into a mass spec and be able to recover it at the end. Okay, so your sample is gone once it goes through this process. So this molecule explodes, and the mass spec instrument basically counts the mass of the pieces that it explodes into. And it's going to blow up in such a way that the more stable the piece, the more prevalent that would be. Okay, so you can get an idea based on how many of a particular kind of piece you had if you have those kind of substructures in your molecule. All right. So we're going to be fragmenting into ions. It's a collection of ions, which will be carbocations, so they're positive ions. And then the machine separates them. And you get a graph that looks like that right there. And what is along the bottom, we're going to draw it here, is this N over Z. And that's along the bottom of all of them. It's a mass to charge ratio. And then over here is the intensity. And the intensity goes from 0 to 100. And the intensity is the easiest one to deal with first. It is, the scale is 100, it's arbitrary. And the machine will just take the tallest peak and set it to 100. So this is set by the tallest peak. And you can see on this particular graph right here that the tallest peak was this one right here. And you come over, that's where the machine said, okay, that's 100% intensity. So it's completely arbitrary, whichever peak's tallest, it sets to 100. Now the mass to charge ratio, that can be affected by the charge on the fragments. You're going to get these fragments, the fragments are charged when they blow apart. And the machine measures the mass of the fragment divided by its charge, which could get kind of complicated if you had pieces that were +1 versus pieces that were +2 versus pieces that might be +3. Fortunately for us, the charge, for everything we're doing, a normal mass spec, it's a plain, boring carbocation +1. And so, that's really nice, because what this x-axis really becomes is mass. So we are going to be looking at it, we're going to ignore the charge part, which is 1. We're going to be looking at those numbers down there as being the numbers that give us the mass of the pieces. So that's a simplification that really makes this work really well. Okay, so it is the spectra of lines that have a certain mass. Okay, so some things you can get off of it, like we talked about, the molecular weight or molar mass of the compound. That would be assuming that once your molecule was hit by the electrons and an electron got knocked out of it, that some actual molecules made it through. You know, we said the electron comes out, you get a radical, and then the molecule goes, right? All of them explode. In order to get the molecular weight of the compound, you have to have some that do not fragment, which happens sometimes. Sometimes it doesn't. You can get the molecular formula of the compound. Your book goes through this process that some people were asking about today, where they give you just the mass spec and say, what's the formula? And it's kind of complicated. When you go through the reading, it's interesting. I'm not going to have you do that, but you can do it. Okay? I'm more likely to say, here's the formula, here's the mass spec, what's its structure, which you can get fairly easily. Information regarding the presence or absence of structural components. That's a fancy way of saying branching. Okay? You can kind of tell where your branches are. So if you probably have an isopropyl group or maybe a T-butyl group, tertiary carbons in there, you can get some information like that. And then you can tie your instrument, and out in industry this is how they do it, the instrument is tied to a database. And so you could inject a sample, say you are in a drug lab, for example, and you're testing, I don't know, samples that the police have collected from someone's house. And you shoot through a particular compound, some white powder of unknown origin, and your mass spec gives you a mass spectrum of it. It's just like an IR. Every molecule has a specific IR, right? And so these machines are tied into a computer database, and they would take the peach you got, zip out, match it to the known things, and say, oh, that was cocaine, or oh, that was flour. You know, that kind of thing. So that's how in industry that those are used, is they tie to a computer database. All right, so let's take a look at what goes on in the actual instrument. We've got a schematic, and we're going to sort of follow through from start to finish what's happening in this poor molecule.
Are these machines expensive?
Yes. Yeah, they are. We don't have one. Okay, so you inject your molecule into the system, which is very sort of GC-like. So you're going to put it in, and it is going to be vaporized. So that is at this point right here. Right here is a probe. The sample is injected in, and it's vaporized. And what happens next, let's just make a list on the board for your notes. The sample is injected and vaporized. And then the second thing that happens is it enters into a stream of electrons. So the molecules are hit by high energy electrons. And they are really high energy. If you look at the numbers there, 6,700 kilojoules per mole. To break a bond, like to completely sever a bond, break it, is 350 kilojoules per mole. So this is more than enough to start to break things in the molecule, start to rip electrons out, things like that. So that is occurring in the instrument where the blue stuff is. Right here it says electron beam, and that's this blue kind of back and forth thing. So the molecules enter this beam, and they get hit by these really high energy electrons. At that point, you knock an electron out of the molecule. So what is going to happen, and I'm going to be drawing it as we go through and kind of do mechanisms of these different functional groups. I'm going to draw it like this. So an electron is removed from the molecule. So I'll be drawing the molecule as an M. And I'll show an electron coming down, flying into it, hits the molecule M, and we will lose an electron out of the molecule. And what's going to happen is the molecule then will have an unpaired electron. So we're going to put a little radical, so it's a radical. And since it lost an electron, which has a negative charge, the molecule is left with a positive charge. So we're going to put a little plus in there. And that is what you initially form. They call this the cation radical. Very inventive. It's cation radical. Sometimes it has a couple of things. They'll both refer to it as the molecular ion. That's because it's an ion, has a plus charge, and it's the ion that comes from the molecule that hasn't blown apart yet. So it's the molecular ion. And when it blows apart, it has all these little fragmented children. Right? It blows apart into these little children. So sometimes they call it the parent. And I'll be using those three terms interchangeably as we go through and talk. They all mean the same thing. It's the very initial electron coming out. As we go through mechanisms, depending on functional group you have, you can tell which electron you'll lose first. And sometimes you can't. And when we want to pinpoint exactly where it came from, like with an alkene, we'll actually draw where the radical is, where the cation is. If we're not quite sure where it came from, and we just want to say, okay, it came from somewhere, we're going to put it in brackets. You'll often see something in brackets like that. And that's where we're being much less specific. An electron was knocked out. And we don't know where, and we don't care. Okay, that's when we're going to use the brackets like that. All right, so we have our parent. It has a charge. And this guy may or may not go through the instrument intact. Okay. If it goes through intact and flies out the end, it gets counted and it shows up as a peak. So if it is intact, it will show up as a peak that will equal the molecular weight of the compound. And oftentimes, some some of them make it through intact. Sometimes none of them do, and there is no parent peak, they call it. Sometimes some of them do, but most of the time the thing goes apart. It's just too unstable. Okay, so this brings us into the fourth thing that happens, is you get fragmentation. And we're going to be doing a lot of mechanisms of this. The parent, which is N plus dot, falls apart. And when it falls apart, we are going to be drawing two pieces always. We'll be having a radical. There's going to be the radical half. So someone gets the electrons apart and it leaves. That leaves behind the part with the carbocation. And you can see here on the slide the two different ways this can happen. This particular thing is showing an alkyl group. Okay, it's an alkyl group with an H on there. And we get this molecular ions, this is the parent right here, and it falls apart two possible ways. One would be where the alkyl group, the R group, gets the positive charge, and hydrogen is the radical. The other way it could fall apart is where the alkyl group gets the radical, and the hydrogen gets the positive charge. And so we're going to see peaks in our mass spec that sometimes correspond to both ways of fragmenting. Okay, so we'll say, well, in one case an ethyl came off as the carbocation, and in some cases the ethyl will come off as the radical. All right, so going back to our instrument, sort of pinpoint where we are. So we have flown through the beam of electrons, and then we got the cation radical, which then goes through and gets accelerated. We're going to shoot it into a tube, this big long tube, which passes through a magnet. And we have to have it moving forward, or it doesn't go anywhere. And so we're going to be accelerating these chunks. Here, it's pieces at this point in time, right in here. So it passes through some charged plates and gets accelerated. And then it shoots into a tube and enters a magnetic field. And that's where things get sorted out. So we've got these pieces. Pieces are accelerated and enter a magnetic field. And here is where they get deflected. So, as far as what is going on in their deflection, here they get sorted out by their mass. Yes?
I see how you would have the ion speed up or accelerated with the magnets over there with the slits.
Mm-hmm.
How would you have the radical part?
You don't. That's the key thing. That what happens with this, and this is where things get simplified, is only the carbocations, so let's just say only the cations, get deflected. Only they get through the instrument. The radical parts don't. They don't interact with it. And so the radical halves are lost in the instrument.
Do they go out the vacuum pump or something? Or?
Yeah, they just do. They just go away. So it's not like you develop a crust inside your instrument and have to go scrape it off every once in a while. But they don't get deflected. So the radicals don't actually pass through this at all. Just the cations do. And they get passed through by mass. When you have a charged particle go into a magnetic field, it gets bent by the magnetic field. And so what happens with the magnet is there is some specific magnetic strength. The beam shoots through the magnet when it's at this specific strength. And what will happen is the pieces will get bent, they'll get deflected. That's why there's this curve in the tube. If you look right through here, the tube is curved. To get through it, the pieces have to bend. And their trajectory has to be bent. And so things that are too light they don't have the correct trajectory to get through. If they're too light, the trajectories bent too much, and they hit the wall, and they don't get through. And so we don't see them. If they're too heavy, that'd be over here. So the ones that are too heavy come up, they just can't get curved quite enough, bang, they hit the wall. They don't get through. You only get, for a specific magnetic field strength, you get a specific mass coming out. And that is where you get kind of your sorting out. So sorting occurs by mass. So what the instrument will do is, of course, in order to get different masses out at different times, the magnetic field strength has to change. It doesn't just set to one strength, because then you would just get one type of piece out. So the magnetic field strength will vary, and it will sort out the different fragments as it varies. So these fragments shoot through based on their mass, the correct mass comes out, and then the minute the magnet strength is changed, what was the correct mass is no longer correct, and it's hitting the walls, and something else is coming through in the beam. Okay, so there's a variation that goes on there. Okay, so by varying the magnetic field, ions of all the masses are collected. They shoot out the end, right here, to a detector, and the detector basically counts them. So it will say, okay, at this magnetic strength, I know pieces that have a mass of 100 are coming out. How many are hitting? It counts them. And then if it changes, well, I know now that pieces that have a mass of 90 are coming out. How many of those are hitting? So it's essentially counting how many hit. The signal from the detector is proportional to the number of ions hitting it. So if very, very few ions of that mass come out, the peak is tiny. If there are a lot of ions of a particular mass coming out, like just a barrage, then the peak's going to be giant because there are a lot of them. So a key thing is the more ions, the stronger your signal, and the taller the peak. So in mass spec, we're going to be paying attention to largely big peaks. It's just like IR. You do not want to try to analyze every peak. We're going to pay attention predominantly to the major ones. Okay? Try to explain what those are. Now we talked about how there's going to be some fragment piece that is going to be the most stable, be the most prevalent, and that's going to give the tallest peak. And so that is what the machine sets to be 100%. So you can see in this particular sample, right here, the fragment that had the biggest peak was this one right here at 41. And it was the tallest one. There were the most fragments of that mass. So the computer said, okay, that's 100%. Everything else is relative to that. One thing to notice here, this guy, if you did its molar mass, it would come out to be 100 when you count up the C's and the H's, blah, blah, blah. Look at that, we got a small peak at 100. So some of these, an electron was stripped out, and some of these flew through intact. Most of them fell apart. I need to give you other things. Okay, so far so good?
So what you're saying is that the shortest peak is continuous.
The shortest peak, there were not many of that particular piece. So for short, there wasn't very much of that. All right, so some facts before we launch into starting to analyze the spectrum. Like we talked about, only cations can get deflected by the magnetic field. We lose the radicals. So we will not see masses for radicals. How the ions behave in the field depends on the mass to charge ratio. That's actually the thing we're really paying attention to, but as I mentioned, the charge predominantly, almost all the time, is +1. So we're really looking at mass. So we're going to be going through and just looking at functional groups. We'll take a look at spectra and try to figure out what piece is it, what cation gave me that particular peak. Okay, we're not going to do them all. One of the things that gets complicated about these is we may, and we're going to run into this probably right off the bat, we will see a really big peak. And we'll look at all our fragments, and no matter how we chop this molecule, we can't get that mass. And it's like the base peak sometimes. And it's a mass that you're just like, where did this come from? what can happen as these things are accelerated through, they are perhaps fragmenting further. Sometimes they can interact with other fragments and make things, and sometimes they can lose hydrogens to form more stable carbocations. So we're going to try in some of these cases to understand why it is, say we think we should get something that's 43, but the big peak is 41. What in the world happened with that? They've got to be related, but something happened in the magnet. Okay, so you do get some side reactions going on. Yes?
There's a few sentences in the book where it mentions which ions are defected to a greater or less extent. Should we worry about that?
Worry about their deflection on the basis of mass, because we're going to assume all the ions are +1. So then deflection is directly related to mass. All right, so we will start. We're going to march through functional groups and just see what they do. That will be the movie, but we're not watching it. So we'll do straight chain alkanes. Boring. You're unlikely to see one of these. There's not too much interesting about them. Mostly because there's no branch point, and so there's no carbocation that really is more stable than any other carbocation. So this right here, and I just want to redraw it. I think it's pentane, right? 1, 2, 3, 4, 5. Okay. So this has a molecular weight of 72. And the first thing that happens is an electron comes in, and we are going to be knocking an electron out of the molecule. With alkanes, it gets a little more complicated trying to decide where it comes from. We'll see with alkenes, it's very predictable. Alcohols, it's predictable. Carbonyls, it's predictable. Almost every other functional group. With an alkane, though, it's all sigma bonds. And so it's tough to tell exactly what electron and what sigma bond you're going to lose. And so what you'll often see in this case would be brackets. You'll often see something like this. And people will just go like that, and they will go plus dot. It's like wherever, who knows? Because all the bonds are pretty much equivalent. What they did in this particular example here, for the purposes of showing a mechanism, is they went and they said, okay, what we are going to do, the purposes of showing what happens in this one example, is we're going to take and have it come from that carbon, and it's going to come from the CH bond. So we had, drawing it over here, we had 2 electrons there originally, and we're going to rip one of them out, and that would be the radical. Now keep in mind that this could be true for this hydrogen here. I could have ripped it from there. I could have ripped it from the CC. I could have taken it from that hydrogen, the CH bond there. And we're going to see peaks arising from all of that. Okay, so this is just an example of one of the things that we do. So we rip that out, and then a number of things can occur. So looking mechanistically, the first thing that we'll do, looking at this guy, draw a little bond in right there. They show taking off a CH3 radical. So I'm going to take the electrons in this bond, and I'm going to do fission, because it's all its radicals. And I'm going to lose a CH3 radical. And what that will leave me with is a carbocation on the other side. I've lost something. I've lost some carbons. Hang on. So this CH2 right here is this CH2 right here, and the other electron ends up there. Okay, so it started off, the piece originally was a cation radical. When I break fragments off, the radical goes with looking at this guy's mass. Just count it up. 1, 2, 3, 4, so that's 48. Plus 3, 4, 5, 6, 7, 8, 9. 57. So that gives us, we should see a peak, if this works, at around 57. In the second example below, what they did is they showed the cation radical, the parent, being created on a different carbon. So they're going to rip out an electron from the middle CH bond. And then they split it a little differently. They said, well, what we'll have now happen is we'll kick off this ethyl portion as the radical. That will leave behind a 3-carbon chunk. So if I start with this guy, and this is plus dot. And I'm going to break off the ethyl as the radical. That will be this. CH3, CH2, CH2 with a positive charge. The mass of that is 3 carbons. 3 times 12 is 36. 39, 40, 41, 42, 43. And I'm getting those numbers just by counting up the mass of that chunk. So, going through and actually looking at the spectrum of this thing, let's see what it actually looks like. I'm hoping I see a piece at 57 and a piece at 43. There it is. So, there are a lot of peaks, right? We're going to do just the major ones. If you take a look at the furthest one, the highest mass one, it is 72. That happens to be this guy. It's the molecular weight, it's the molecular ion. That piece at 72 is the cation radical. Then we see 57. You guys see that there? That's the 4-carbon piece that we got by losing a CH3 radical. And then we lost the ethyl. That gave us a piece at 43. We see that. What's going on with the 29? The 29 is, it's an ethyl, yeah. Remember we talked about when you have the cation radical, it could cleave either way, right? So this way I chose to break off an ethyl radical and have the larger chunk be positive. Well, it didn't have to be that way. I could have broken it like this. CH3, CH2, CH2 radical, and had the ethyl break off as the carbocation. Could have just as well fragmented that way. That would give us 29. And then at 15, what do you see? A CH3 plus. How likely is it to have a CH3 plus? Have we run into one in synthesis? Yeah, this is not very stable. And so, notice the peak's kind of small. So with an alkane, you just basically start chopping off carbons and leaving behind carbon ions. A couple things to notice about it is, you look at kind of the shape going from the light ones to the heavy ones, there is sort of a bell-shaped curve. And that's going to be true with alkanes, non-branched straight chain alkanes. You get this bell-shaped curve to it. The chunks that you lose correspond to chunking off CH2 groups. So what we have here is looking at the, where's my, there it is. Looking at the parent, right here at 72. We lost a CH3, right? Kick that off first. And so that took us down to 57. Then as we break our way into the molecule and break off more and more pieces, the only thing we can crack off is a CH2 right there. That gave us that. So the difference between 57 and 43 was 14. That's that CH2 breaking off. Then we get this piece that's 3, chunk off another CH2, lose 14, we're down at 29. So what you end up doing is you break an end off, and then you start going minus a CH2, minus a CH2, minus a CH2. So it's very distinctive that the difference between the major peaks is 14, which is that CH2. And then, with the bell-shaped curve, obviously the higher part of the bell shape is the most abundant pieces. They're the ones that are the larger fragments. That's just a probability issue. I'm going to have fewer fragments that are smaller because I only have one way of breaking off the CH3. But I have a couple ways of breaking off the ethyl. And so there are more ways to create fragments of kind of an intermediate size than really small ones or really large ones. And so statistically, you're going to have more intermediate sized pieces. All right, let's look at another one that's a little bigger. What's that?
Why do we have like the different lines
Around
around
the 43?
or like, several different lines for each?
Oh, let's go ahead and tackle that now. The question was, why are there several different lines around things? As an example, if you take a look at this 43 right here, which was this propyl group, notice there's a few below it. There's like a cluster around it. What you're going to find is that is sort of relatives of that initial fragment that came through. It's going to be really common for, let's go up to this guy right here. This is at 43. You almost always see with a propyl or an isopropyl group, you see something coming over at 41. And what those typically are, the things that are clustered around a peak are where you have gained or lost hydrogens. And a 43 almost always comes with a 41. What's gone on there is you have lost 2 hydrogens. And that is as that fragment is flying through the instrument, it's doing things. And what in this case it's doing is this. What would be the advantage of losing 2 hydrogens? It forms an allylic carbocation. And so it's things like that that are causing the clustering around a particular peak. And it also makes analysis a little bit tougher, because then you got to try to figure out, well, what is this thing that doesn't match any of the pieces? All right, let's look at hexadecane. One right there. So, hexadecane is big. The formula, erase all this, we have some room to work. C16H34. So, in terms of its mass, we have 16 times 12 plus 34 times 1. I worked this out ahead of time for you. 226. So an electron hits this nightmare, and I'm not going to draw it. C16H34. It's hit by a high energy electron. It loses an electron from somewhere, various places. And we get this. C16H34. And I am going to be very non-committal and put it in brackets. Now, this is the parent. At this point, I have lost just an electron, which weighs effectively nothing. And so this has an M over Z of 226. So, that's my molecular weight. And do you see it in there?
Right.
Yeah, it's right there, it's the highest mass. So whenever I got a mass spec back, I would know what my molecular weight should be of what I thought I made. I would zoom right over to the highest mass and check it out. That's what everyone does. So, there it is, right there. There's my molecular ion peak, right there. It is tiny, right? What does that tell you? The fact that it's tiny. Yeah, most of this molecule blew apart into pieces. So what we should see, if everything is true, is we should see minus a CH3, and then minus CH2, minus CH2, minus CH2, minus CH2, and on and on and on we go. So, I see questions.
Those 226 wasn't there when you were looking for it.
Oh, it's okay. It just tells you that your molecule completely blew apart, and there was no detectable parent. So often, sometimes it's there, sometimes it's not. And if you see it, it's like, yes. And if you don't, oh well. Then you have to start looking at fragments.
It would be like you see the fragment, like you think it's the biggest mass, but there's actually more.
There's something higher.
Yeah.
Then, if that occurs,
You don't know that.
well, if that occurs, you have two things that could have happened. You made the wrong molecule, okay? Or you might have isotopes will do that. Because it's measuring masses, and isotopes cause things to have different weights because neutrons are heavy. Okay, so it could be isotopes as well. And we'll tackle those probably next time. I saw a question. Got an answer? All right, so let's go ahead and let's see if we see the pieces. If we do minus CH3 as a radical, that would leave me with a chunk that would be 226 minus 15, right? I don't want to draw it, I'm too lazy. So 226 minus 15, that would leave me a piece that would be, what is this? 211. And do we see anything like that? No, okay, but not to panic. What else do we have? 197 is small, then we have a 183. What's the difference between 197 and 183? 197 minus 183 is 14. Well, there you have it. So we're starting to dig into the molecule. And then 183 minus 14, what would that be? That's another CH2. What would that be? 169? Do we see a 169? Lo and behold, we do. And so you can see, losing the CH3, we really didn't see that. It must be a really small piece. But then we're going minus the CH2. We're just chunking off sections of that molecule. Okay? You guys see the bell-shaped curve? It's skewed towards pieces that are 3, 4, 5 carbons big. So if you look at that bell curve, it's right here is where it's really tall. 3, 4, and 5 carbons. That's because there are a lot of ways of getting 3, 4, and 5 carbon pieces out of that molecule, different combinations. Okay.
You mentioned that methane as a carbocation was unstable, but it seems like in this graph that even a 15 carbon chain that's a carbocation is not stable, or less stable.
It's showing up. It showed up the CH3 plus. Right
Yeah,
there.
yeah, that shows up there, but like, why is it that if you have a 15 carbon carbocation, why isn't that stable enough to show up?
Oh, as far as, I don't know. I don't have an answer for that. It must have been, for whatever reason, not much of it. I don't know why that minus CH3 didn't show up. Just didn't.
Okay.
Don't know. I don't know why a piece that would be 14 carbons is better than a piece that's 15.
Is it possible for something that's really big like that to get kind of double bombarded? Like it'll break apart and then one of the fragments will get hit as well?
Well, if that happened, you'd end up with a +2. I don't think so, because once the electron beam hits, you make the parent, and the parent starts traveling. So it can't get double bombarded because the electron beam is in behind it. So once you create that carbocation, it's moving onwards, and there's no more bombardment moving on, which is good. Okay. A little more interesting than just chunking off CH2 portions is where you get into things that have branched. So that'd be your branched alkanes. Now, with these, it is less likely that you will see a parent, because with a branched alkane, fragmentation at branch points is really common. If you have fragments at branch points, you end up with, for example, something like that. What do you see there? Tertiary carbocation. So if fragments at branch points, that gives you secondary and tertiary carbocations. And those tend to be pretty stable. And so we're going to see big peaks for fragmenting at branch points. And those tend to occur pretty readily because they're more stable. And so your parent, when you initially form it, tends not to last. And so with these, you don't really panic if you don't see a parent. You might, and you might not, and that's okay. So, looking at the particular molecule we have there, 2,3-dimethylpentane. Let's take a look at it and see what kinds of things can happen to it. And then try to identify some pieces. So, it looks like this. Okay. And we're assuming that we have hit it with a high energy beam of electrons, and we have knocked an electron out at this point in time. And once again, it's all sigma bonds. So we're being very nondescript about where that electron came from. It's really hard to predict. Okay, so the first thing has a molecular weight of about 100. Do we see a peak at about 100? Yeah, it's tiny, but it's there. Super tiny. Okay? But right there is the molecular ion peak at 100. So we do see that. Let's take a look at the fragments that we might expect to get from this. I might expect, and let's get a different color pen. Let's use red. What if I cleave right here? If I cleaved right there and took off an ethyl radical, so minus CH3, CH2 radical, I would have this. Right? That's secondary, so that's not totally beyond the realm of what I would expect. As far as its mass goes, I can sit there and count up the carbons and hydrogens and this and that, but it's a lot easier if you do this. Its mass, its M over Z, will be what it started with, 100, minus the chunk I lost, right? What's an ethyl weigh? 29. So 100 minus 29, that has to be what?
71.
71. Do you see a peak at 71? Yeah, it's tough. Nothing's labeled here. I tried to label them on the test for you because it's hard. 71 is this guy right here. It's called. That's your 71. So that's good. We did see that. Another place we could lose something would be, what if I cleave right there? I may or may not see it, but it would give me a secondary as well. That'd be losing just a stage 3, right? So let's say I do that. And you might not see all these, it just depends. So I lose a CH3, that will give me this, and put the plus right there. That would be 100 minus 15, 85. Do you see anything at 85? Yeah, it's not really big, but it is there. It's right there. That little guy there is 85. That fragmentation wasn't as favorable. It's a secondary carbocation still, but what do you think the problem is that would make it smaller? You're making a methyl radical, which is not the most stable thing. And so this one is not as favorable. Most likely because a CH3 radical, not so great. What else do you think?
You can cut off at 43, like.
Yeah, I could cut off right there. And if I cut off right there, I could get, so this would be minus this piece as a radical, right? And it would give me the isopropyl part as a plus. That might be easier to count forward on this one. So if this is actually, it's a CH3 up here, and what is this thing? CH. So what are we looking at there?
42.
Let's see, 36, 39, 40, 43. Do we see anything at 43? This is like a cluster, right? I see a cluster. But if you count, here's 40, nothing much going on there. 41 is kind of big, but I don't want that one. 42, there's something. Look at 43, it's this big one right here. That's 43. There. So what I see this, it's large. I see 41 large also. What's going on with that? They've got to be related.
There's 2 hydrogens.
It's, I lost 2 hydrogens, and the thing at 41 is this guy. So it made an allylic carbon cation. And you'll almost always see that. Clusters around groups like that, where things are challenging. We haven't tackled this. We haven't tackled this stuff right below 60. Right? There's obviously something important going on there. What do you think that is?
It's the half side.
It's the other half, exactly. I chose when I wrote it in between the isopropyl and that large chunk, I chose to take the large chunk off as a radical. It could have gone the other way too, right? I could have done, let's go backwards this way with it. Go over here. I could have taken off that isopropyl as a radical, and I wouldn't see it in that case. I could have done like that, and this. So this piece, the carbocation at 4, that'd be 100 minus 43, 57. And it's that big peak right there, 57. And then there's clusters around it where it's starting to lose hydrogens and different things. But we do see something at 57 with a grouping around it. Okay? The thing at 29, what's that?
It's an ethyl.
It's the ethyl coming off as a plus. Not as prevalent, it's just not as stable. All right. Questions on branch? Okay. The last of the alkanes, cyclic. Cyclic alkanes have a couple of common fragment patterns initially that can help you identify them. And then you just kind of have to fish around in the dark hoping you can figure out what's going on. They're not quite as nice. But 2 things that happen with a cyclic that's pretty common. If you have a side chain, like the particular example we have up there is a cyclohexane with a propyl group on it. If there is some sort of an alkyl side chain, that tends to be lost easily. So one of the things we will look at right off the bat is we will look for some sort of piece where we have a peak right there. Okay. So let's go ahead and let's do that and see what we see. This is 126. And I'm going to lose. Let's go ahead. Let's put this guy in brackets and go plus dot. They start from the right place. So we'll start with the parent. Yeah, good.
Doesn't matter, it's up there, it's only using 2, but the
Which one?
For the equation shows this lives in 2 carbons, but the molecule actually has 3 carbons in the chain.
Oh, yeah. On this one, this must be, I suspect that's probably an ethyl.
It's
there,
C2H4.
And our example we're gonna do is the 3. Okay. So, we're gonna lose the 3 carbon piece, and we're gonna do the actual spectrum down below. And that is going to give us, and we're gonna be again very nondescript about where it's coming from. It's going to give us the ring as a carbocation. And then what we will have, we will have broken off this piece right there. Propyl ring. So the ring as a carbocation should be 126 minus 43. And what does that come out to be? I should write it.
83.
83. You guys are good. So looking at our spectrum down below, you see something at 83? Yeah, it's pretty large. It must be at 80, 81, 80, it's this big one right there. What's this right here? Is that one right there?
Parent.
That's the parent, yeah. Okay, now, so what will first happen is if you have a ring and it has things on it, the things that are on it crack off. So you look for give you just the ring piece. And then what tends to happen is the weirdest thing ever is that the ring itself breaks out a 2-carbon fragment. And this is really odd. I have to see if I can even get the mechanism and arrows right on this one. So, what we are going to have, let's see if we can do this, is we are going to have a ring right there. And the ring has, oh, this is what this is referring to, plus dots. We cracked off the 3 carbon piece. Now what is going to happen is we are going to break out right here and right here. It breaks out 2 connected carbons. And what we have is we have minus CH2, CH2 dot. So that is this portion right here. That's the C2H4 that you were seeing. Yes?
So like, when that propyl group breaks off, there's obviously, that carbon on the ring, that's just a CH by itself.
It is just a CH,
That one
exactly.
doesn't break off like in this part.
Right, so what we have, this right here is a CH at that point.
So shouldn't it be minus CH, CH2? Or?
Let's go ahead and yeah, I want to actually leave that piece there. I'm pretty sure. I want that CH to be there. Let's go ahead and let's break it somewhere else, because it does lose a CH2, CH2. So if we broke our propyl there, let's chunk that out. Okay, I'm going to lose a CH2, CH2, that's what it does. You end up with, here we go. Here's a CH, here's a CH2, so that's kind of the ends. I'm looking right there, and right there, there and there. And what's on is out like this. I have 2 electrons there. And I have plus right there. So I had cation radical, or cation, break up a radical, and I get this. So you lose a chunk of the ring out. And this guy's mass is what? 83 minus, what's it going to be?
So it's going to be 30?
Let's see. Here's 24, 25, 26, 27, minus 28. What are we looking for? 55?
Yep.
Yeah, I think, isn't that right?
Yep.
Do you see anything at 55? this piece is where you broke off the side chain and then ripped out the CH2 from the ring. Okay.
That one you will,
Huh?
that one will have two pieces then?
You would have it
Because-
fragmented into 3 pieces, exactly.
Yeah, okay.
Yep, the fragments into 3 pieces total. So, let's see. I guess that's about it. What about the piece of 40? What else is there? 42, 43. What do you think that is?
Side chain.
That's a side chain. Yeah, it is fragments. Okay. What time are we done out of here? Like right now?
3 minutes ago.
3 minutes ago. Okay, next time is alkenes, benzene, carbonyl,